Okay, let us talk about a position vector. Okay, so in physics, we need to find the position of a particle or a body. All right, and usually, whenever we find a position, we have to denote with what point, with respect to what reference, we need to take the position of that particle. In general, the position of a particle is measured with respect to the origin. For example, let's say we have this coordinate system out here on this xy plane. Okay, so let's say that is the y-axis and this is the x-axis, and this point here is the origin. So we imagined a particle to be going from point A and it is traveling to point B, let's say. Okay, for example, a small insect or an ant, let's say. All right, so this ant or that insect is going from point A and then it is walking, and finally it reaches point B. So do you agree or not, the position of the ant is changing with time? No, it is changing with time, right? So how do you know that it is changing with time? Suppose the ant is somewhere here. Okay, how do I draw an ant? Let me see if we can. Let's say this ant is something like this. Okay, if the ant is somewhere there, then how do we know the position of the ant? We just draw a line. We just draw a line from the origin to that point where the ant is at that particular instant of time. All right. So if this ant now has come to this point, then if we draw a line from the origin to where the, let me use a scale. If we draw a line from the origin to where the ant is, we get another position, another line like this, okay? And always we have to put the arrow mark. So these lines, they are nothing but the position vectors. Okay, the position vectors. Let's say if the ant is at point A, then you can simply join from the origin to point A. If the ant reaches point B, you can simply join from the origin to point B, right? And the direction is always directed from the origin to that position where the particle is. So as the particle is going like this, okay, you can have, let's say in the when time is 0, it is here. When time is 1 second, it reaches there. When time is 2 seconds, it reaches there. When time is 3 seconds, it reaches there. So from here, you can have multiple lines at many time, okay, at many instant of time. So these lines which are joined from the origin to the position of that particle at that particular instant of time, these lines are called the position vectors. Understand? So basically, what is a position vector? A position vector, it is a vector which denotes the position of a body with respect to the origin at a particular instant of time. Okay, it is directed from the origin to that position of the body. All right, let me draw a different diagram here. Okay, so let us find the representation, the mathematical expression of this position vector. Let's say we have the coordinate axis just like before. This is the y coordinate and that is the x coordinate. Okay, and let's say this body is going from it's going from point A and it reaches point B. All right, it's going in that direction. Okay, and at any particular instant of time the body is at point P. All right, so what is the coordinates of point P? X, Y. Okay, this is on the xy plane. So if you join a line from this point, from the origin to the position of the body, this gives us the position vector. Let us denote the position vector by r bar. Okay, all right, now what we do is we drop a perpendicular from this point P. We drop a perpendicular here on the x-axis, and we drop a perpendicular from point P on the y-axis. Okay, so let me just give some dotted line like this. All right, so do you agree or not that from here till here this gives the value of x, and from here till here this is the value of y? Okay, let us name these points as A, B. Let's call this point C, and let's call this point D. All right, so now let's say, do you agree or not? If you look at this diagram, it can be drawn like this. Okay, let's say, let me draw a smaller diagram out here. So that is point P, and this will be x, and this will be y. Okay, so this is point P, this is point O, this is point C. So this is the vector r bar, right? And if I go this way, that will be the vector x bar. Yes, because I'm going from here this way, and if I go from here up, and this length is equal to this, so this will be the vector y bar, is it not? So if you look at this figure 2, let's call this figure 1. So if you look at figure 2, in figure 2, do you agree or not? Now just listen here carefully. Just listen carefully. If you go from O to P, that means OP bar, this will be the same as going from O to C and then C to P. You will reach the same point. Yes or no? Right? Just have a look at this diagram. OP is the same as going from OC plus CP. So in vector language, we say OP bar is equal to OC bar going like this and CP bar plus CP bar. Do you understand or not? But what is OP bar? OP bar is R bar is equal to OC bar, here is X bar plus, and CP is Y bar. Yes? So this implies R bar is equal to, now X bar, I can write it as X into I cap. Yes? Y bar, I can write it as Y into J cap. Okay? So this here, it represents the position vector in the xy plane. Understand? So that is the representation of what? Of the position vector. Okay, now this vector, you can see here, this vector, so that is why you have x, which is the magnitude, and I cap here is the direction, y is the magnitude, and j cap here is the direction. Now suppose if you want to find only the magnitude of this vector r bar. Now again, what do we mean by magnitude? By magnitude we mean the length of r bar. So in other words, the length of this line OP. Okay, so that to so if we find the length of the line OP, we can get the magnitude of the vector r bar. All right, so how do we find the magnitude here? It's very simple. This is a right angled triangle, is it not? Now if you this will be the hypotenuse, perpendicular, and that will be the base. So it's very simple. Using Pythagoras theorem, we can find the length of this hypotenuse. Okay, so in figure 1, or let's take figure 2. What do we have here in figure 2? This one. Can we say that OP square by Pythagoras theorem, is it not OP square is equal to what? Is equal to OC square plus CP square. Is equal to OC square plus CP square. Yes? Okay. But what is OP square? OP here is R, right? R magnitude. Yes, because I didn't write here OP bar. So that means when I write R also, I have to write only R without the bar sign. So that will be R square. And OC here, there is no bar sign, right? Because this is just the length of OC. Okay, so that will be X square plus CP here will be Y square. All right, so R is X square plus Y square under a root. Yes, and what did I tell you? Whenever you write a vector without a bar sign, it represents the magnitude, okay? Which is the magnitude of the position vector. Is it clear? As a note, in 3 dimension, okay, the position vector is written as R bar is equal to X I cap plus Y J cap plus Z K cap. And what will be its magnitude? Its magnitude is R. Remember, I told you I can write R bar modulus or simply R. That represents the magnitude. So this will be what? Let's just have a look before. So whenever we take the magnitude, we take X square plus Y square under root. Yes or no? So similarly here, there will be one extra term. So that will be X square plus Y square plus Z square under a root. Okay, we don't need to calculate this one. We can just generalize it. Got it? So that is the position vector. So let us see once again, what is a position vector? What does it determine? It is a vector which denotes the position of a body with respect to the origin at a particular instant of time. It is directed from the origin to that position of the body. Okay, and how is it represented? It is represented by this in 2 dimension on the XY plane. All right, and what will be its magnitude? How do you find the magnitude? So magnitude will be just coefficient of I cap, that is X square, plus coefficient of J cap, that is Y square, under a root. Okay, and in 3 dimension, the position vector is written like this. There is an extra term, and that is the magnitude.